Here, this is a video lesson on the law of cosines. I'm going to begin by making a diagram of a triangle, and it's going to be a generic triangle, so that what we use it for, what we derive from it, will apply to any triangles, all triangles. I'm going to label the vertices of the triangle A, B, and C, and the opposite angle A is side A, the opposite of angle B is side B, the opposite of C is side C, and a line perpendicular inside the triangle from angle B perpendicular to side B we'll label as height, which then makes two right triangles inside of the greater triangle. And the side B, since it was intersected with the height, I will then distinguish between the two line segments that were created as D and E. So here's something that is observably true. The length side B is the sum of what's been labeled as D and E. Also, observe from this diagram, I can solve for E by subtracting D from both sides, a simple change. And it created, by drawing the height, two right triangles. The Pythagorean theorem applies in both cases of these right triangles with its relationship between its sides. So I could write h squared plus d squared is equal to the hypotenuse of this right triangle, a squared. And similarly, relating the sides of h, e, and c in this right triangle with the Pythagorean theorem gives me h squared plus e squared is equal to c squared. I could change these Pythagorean theorems and solve both of them for h squared by subtracting d squared in the first case and e squared in the second. So the first equation, h squared, is equal to a squared minus that d squared. And in the second Pythagorean theorem, I can solve for h squared by subtracting e squared from both sides, which gives me h squared is equal to c squared minus e squared. And since these two new equations are both solved for h squared, then their expressions are equal to each other, which allows me to write and bring them together into a squared minus d squared, that's the first one, and then substituting in for h squared, I could say this is equal to c squared minus e squared. This equation here, I'm going to solve for c squared by adding e squared to both sides. When I do, I get c squared is equal to what was on the left before, a squared minus d squared, now plus e squared. Next, I'm going to take what e is equal to up here, and I'm going to substitute it in for e in this last equation. When I do, I get c squared is equal to a squared minus d squared plus, now instead of e, what e is equal to is b minus d all squared. And now I'm squaring a binomial. I'm going to go ahead and distribute this, multiply b times d by b minus d by itself. So the c squared is equal to a squared minus d squared is weighting, and I'm going to add this expansion, which is b squared minus 2bd plus d squared. And I can see that I've got a minus d squared term plus d squared term, which can combine and cancel. Next, I'm going to write c squared, and after I have canceled those terms, I have the a squared plus b squared minus 2 times b times d, which is a nice expression to have been based on this triangle. It contains sides C, A, and B is represented a second time, but it also contains D, and D is only a part of the side or one side of the triangle. It would be helpful to eliminate D if I can. I can observe that D in this right triangle shares or is a part of the cosine ratio. The cosine of angle C is equal to its adjacent D over the hypotenuse A. I could write that down. The cosine of angle C is equal to the adjacent D over A. And I can solve for D by multiplying both sides by A. When I do, D is equal to A times the cosine of angle C. Now, side A and angle C are parts of the triangle. So if I substitute that expression in for D here, then I get c squared is equal to a squared plus b squared minus 2. Now substituting in for D, a times the cosine of c times b to finish up. This equation here has 3 sides and 1 angle, but they all belong to the triangle. And the triangle is general in that we can label any triangle with sides A, B, and C and angles A, B, and C. So this equation works for all triangles. This, when it was discovered, was so useful for expanding the knowledge of a triangle by being able to relate 3 sides and an angle that they called it a law, the law of cosine, or the law of cosines. The word law doesn't make it any more special than any other mathematical relation or truth in mathematics, but it was so impressive when it was discovered that they used that word. Let's use it in an example. A triangle has sides 3, 4, and 6. Find the angle opposite the side 4. Always useful when given the description of a mathematical situation is to draw a diagram and label it with everything that we can. I'm going to draw a triangle. It's generic. It wasn't meant to look like a equilateral triangle. But if I label it with the given side measures, obviously it can't be an equilateral. And I'm expected to find the angle opposite side 4. So here's the side 4, the angle opposite it, I will label with a theta. Now, I have in a triangle 3 sides and 1 angle that I'm trying to find, which are the variables that are represented in the law of cosines So it's the law of cosines that I'm going to use. And note that the law of cosines, as all formulas and equations are capable of doing, can solve for any of its variables as long as we have values for the remaining or the other variables. The fact that the angle in the law of cosines is here inside of this expression doesn't mean that I can't use the law of cosines. There's an impression that when we use formulas, they're only for the variable that is solved for. But that's not true. In this case, I'm going to set it up with this capital C as the unknown. Now, these C's share a relationship. They're not the same symbol because one is capital and one is lowercase. But they're both C's to show the relationship that they are a side angle opposite pair. And when you use the law of cosines, the numbers or the values of the triangle that those are the position of must be a side angle opposite pair. So observing what sides and angles I have, the angle that is going to go into the cosine for C is theta, which means that the side C on the other side of the equation must be the side opposite it with a measure of 4. When I use the law of cosines, I typically write the angle and the opposite side first. And then I'll fill in the rest of the law of cosines. So the 4 squared, the side of 4 squared, will be equal to side A squared plus the side B squared. These other two sides, 3 and 6. And it doesn't matter which is A and which is B, it's the same in either case. So I'm going to write 3 squared plus 6 squared minus 2 times that side A again times that side B again. So I have plugged in my values into the law of cosines. There is one unknown theta. It's that angle that is opposite the side that was chosen here to be 4. And I'm going to solve for theta. 4 squared is 16. 3 squared is 9. 6 squared is 36. 2 times 3 is 6, and then times 6 again is 36 times the cosine of theta. Now in this next step, mistakes are very often made. I can see that I have plus 36 and a minus 36. So it's very common to quickly combine those and eliminate them, or combine those two numbers even if they're not equal and opposite sign. But we can't because the 36, or whatever this number is, the product of 2, 3, and 6, 2a and b, is still multiplying the cosine of theta. And we have to multiply before we subtract. So don't make that common mistake. Do not subtract the numbers in this position. You can't. This number is multiplying still, and this number is not. So I'm going to take the 16 and subtract 9 from both sides, and then subtract 36 from both sides. And when I do, I get negative 29 is equal to what remains, a negative 36 cosine theta. Now dividing both sides by negative 36 will give me, and the negatives will cancel out, 0.80556 is approximately equal to the cosine of theta. Because I haven't finished with the problem and I had to approximate 29 over 36, I did so with many decimal places so that I am as accurate as I can in the end. The last thing I need to do to get theta by itself is to undo the cosine function. The inverse of cosine is literally called inverse cosine. So I have to take the inverse cosine of both sides, or a cosine of negative 1 is the symbol for inverse cosine. Inverse cosine undoes cosine, leaving theta by itself. And we'll need to rely on a calculator to find the inverse cosine of 0.00556, and that's approximately 36.336 degrees.